Hi everybody, welcome to video notes 10.3. We're going to talk more about the properties of acids and bases, titration, neutralization, and different compounds that turn into acids and bases when you put them in water. Okay, there's a lot of cool things in your books. Chapter 16 has some pretty interesting articles. Alright, so neutralization reactions. Hopefully you see the word neutral and think water, because a neutralization reaction is when an acid and a base make salt in water. So sulfuric acid is H2SO4, and that's going to be aqueous. Reacts with sodium hydroxide, which is NaOH. How do I know? +1, -1, NaOH. Alright, so it's going to form water, so let's put that down. And it's also going to form a salt with the cation of the base and the anion of the acid, but have to cancel charge. So sodium's a +1, sulfate's a -2, so it's got to be Na2SO4, and that's also going to be aqueous. All right, and then we got to check to see if we need, okay, so I got to put 2 there to get 2 sodiums. And now I have 1 sulfate, 1 sulfate. I have 4 hydrogens, so I put 2 there, and I have 2 oxygen, 2 oxygen. Okay, hydrochloric acid, HCl, reacts with potassium hydroxide, KOH +1 -1, KOH, to form water and salt. So let's do the water over here. And it's 2, of course. And the salt, so we have +1, -1, so it's going to be KCl. And we check to see if it's balanced, and it is. Hey, here's one for you to try. Alright, so we use neutralization reaction in a technique called titration. And titration is used to figure out the concentrations of solutions. So we take an instrument called a burette. This is what it looks like. You can also spell it URET. It measures the hundredths place in the volume. And so you rinse it and then you fill it with the substance you're going to use. You open this to let the air bubbles out, not into here, but you drain it a little bit. And then in this beaker or flask, you add an indicator and a different solution. You record the volume of the amount you put in here, record the volume of the amount you start with in here, and then you add some of this to here until this changes color. So why does the color change? Well, we put the indicator in there, and it's reached a certain pH when the color changes. That pH happens because of the equivalence point. The equivalence point is when you have equal amounts of hydrogen ion and hydroxide ion. Why? Because that gives you water. How are they equal? Well, you get moles of each that equal each other and you get water. The end point of the titration is when the color changes. So, equivalence is, we said, when moles of hydrogen ion equal moles of hydroxide ion. And then we're measuring them in concentration, though, so it's moles per liter. So we have to get moles, and moles have to be equal. So we have to multiply the molarity times the volume, and look what happens, we get moles. So if you measure the molarity of the acid and multiply by the volume, and know the amount of H plus, it should equal the amount of molarity of the base times volume of the base and the amount of hydroxide ion. So let's look at what these variables mean. Ma is molarity of acid, that's the concentration. And Ba is the volume of the acid in liters or milliliters. Okay. H plus is the number, it's just a number of acidic hydrogen. Okay. Mb is the molarity of the base. Vb is the volume of the base. And OH minus is the number of hydroxides that are being neutralized. Number of hydroxides. So how do you get this part? That's the new thing. For instance, if you have HCl, H equals 1. H2SO4, H equals 2. And so you just count the number of H's. If you have MgOH2, OH equals 2. If you have AlOH3, OH equals 3. So you just count and plug that number in. So here's how the technique works. Again, you put the solution, one solution here, one solution here. Measure this one, add some of this into here, and then the color changes, and then you can do some calculating. So let's list out our variables. So what's the molarity of the acid? 0.25 molar. What's the volume of the acid? Well, it's 0.025 liters. What's the number of H's in the acid? Well, we have to look at the acid is H2SO4, so this is going to be 2. What's the molarity of the base? That's what we're looking for. What's the volume of the base? It's 0.075 liters. And what's the number of hydroxides in the base? Well, it's NaOH, so OH equals 1. So we've done the formula, and plug it in. 0.25 molar times 0.025 liters times 1 hydrogen in the acid equals the molarity of the base times the volume of the base times the number of hydroxides in the base. So the hydroxides is 1 and the hydrogens. So when you solve for x by dividing, you get x equal to 0.25 molar times 0.025 liters. Number 2 moles of hydrogen. 0.075 liters. And notice the liters cancel. You're left with 0.167 molar. What about this one? Well, again, NADH plus equals NADH OH minus. It's the formula. The molarity of the acid is, we don't know. The volume of the acid is 0.025 liters. And the number of H's in the acid is, it's the one of them. Molarity of the base is 3 molar. Volume of the base is 0.035 liters. And the number of hydroxide in the base is 2, because there's 2. Then you plug it in again. Something else, we'll do it. Something else. 0.035 liters. And 2 hydroxide. So X ends up being 8.4 molar. So acids and bases make salts. So let's analyze the salts a little bit more. Salts come from acids and bases. The cation part of the salt comes from a base. So this must have come from NaOH, which is a base. And it's strong. The cyanide part, the anion, came from an acid. That acid must have been HCN, which is an acid, which is weak. So the part of the acid or base, if there's a weak part of it, or if it came from something weak, then that can get further hydrolyzed in water. So let's put it into water and see what happens. Hydrolysis. This is called salt hydrolysis. Salt hydrolysis. Because we're taking the salt and hydrolyzing it with water. Okay. And so that's going to turn into HCN, which is a base, and OH minus, which is a. So when sodium cyanide gets hydrolyzed, base forms. So this is a basic salt. Basic salt. All right. This is ammonium nitrate. The ammonium came from a base called ammonia, which is weak. And the nitrate came from an acid called nitric acid, which is strong. So when it gets hydrolyzed, the part of it that is affected is the opposite of the weak acid. I'm sorry, weak acid, I said. It's the base part that gets hydrolyzed. So NH4 is an ion, gets hydrolyzed, in water, and it then turns into NH3, which is aqueous, and H3O plus. So when ammonium nitrate gets hydrolyzed, acid forms, and so ammonium nitrate is an acidic salt. Acidic salt. This came from KOH, which is a strong base. Where did this come from? It came from sulfuric acid, which is a strong acid. And so neither of these came from a weak conjugate. So if this one is going to form a neutral salt. Neutral. All right, so salts can hydrolyze and make your solution turn acidic, basic, or neutral. The key to knowing it is you look at where it came from. So if it came from strong acid and a strong base, then it's going to make a neutral salt when it hydrolyzes. Either acid or base will form when it hydrolyzes. A salt from a strong acid and a weak base is going to make an acidic salt. A salt from a weak acid and a strong base is going to make a basic salt. So, what if a salt comes from a weak acid and a weak base? Well, they're not equally weak, and they have different Kas and Kbs, so we don't know with that one. This is unknown. Right? But these ones, we can show the work for and test. Okay. One more kind of thing. That thing's called an anhydride. Anhydride means without water. So metal oxides are base anhydrides. So what's a metal oxide? So it's an oxide that starts with a metal. And we'll call that metal M for metal. Right? So any compound that starts with a metal and then is with oxygen. That's what a metal oxide is, oxygen. And so metal oxides, we'll give some examples. CO2, NO2, SO3. And we'll just go with SO2, all right? And so what they do is they react with water to form an acidic solution. And so metal oxides can cause acid rain because these are all pollutants, right, that come from factories and cars and other stuff. Right? So why can't base anhydrides fix acid rain? If we can get acid rain from metal oxides, non-metal oxides are, we'll say NM, non-metal oxides, non-metals, are called acid anhydrides. Well, I just totally messed this up, didn't I? Did anybody look at this and say, Harbin, that's not a metal? All right, so I'm going to switch them. No, I'm not. Come on, this is forever. And I'm not retaking this. So, a metal oxide would be something like magnesium oxide, MgO. Metal plus oxygen, see, metal. All right. Another metal oxide would be sodium oxide, so it's a metal. And these are base anhydrides because when you put them in the water, they turn into bases, which makes sense because these are both from group 1 and group 2 on the periodic table, and when you put them in water, they turn into sodium hydroxide and magnesium hydroxide. Okay. Non-metal oxides are things like carbon dioxide, sulfur dioxide, and nitrogen dioxide, and they turn into acids when you put them into water. So they're not acids or bases by themselves, but when you put them into water, they turn into acids or bases. Whoa, glad I got that on the right track. Probably made this video a little longer, but hey, we're getting through it. So, anhydrides react with water to form acids or bases. So this is a non-metal, and it's an oxide. And so when you put it into water, carbon dioxide, it's going to be a gas, goes into water and forms H2CO3. So this is an acid. So we call this an acid anhydride, which is a non-metal oxide. Okay. Barium oxide is a solid. So most of your metal oxides are going to be solids because they come from metals and oxygen, and those make solid compounds. And you're going to get very okay. And so then you have to put in the 2 there, and the 2 there, and 2, 1, 2, 3. Was it finished? 2, oh, it was already done. Well, Tato, you were supposed to help me balance it. Okay, so you can see that so this is a base anhydride. Because when you put it into water, it turns into this. Alright, so see how these gases coming from, and then this also produces CO2. Then they turn into acid, and then those get deposited. Okay. Here are some effects of acid rain. Alright, breaking acid strength by Ka. Which acid is the strongest? Well, the one with the biggest Ka. So that would be H. 3PO4 on this list. On this list. So powerful acid is a weak conjugate. So this is the strongest acid, so this must be the weakest conjugate base. And what conjugate base is the weakest? H2PO. What conjugate base is the strongest base? So that means since this has the smallest Ka on the table, it's going to have be the strongest base because it comes from the weakest acid. Okay? So the trend is the stronger the acid, the weaker the conjugate. The weaker the acid, the stronger the conjugate. Okay, just to review, acids and bases make salt and water. It's a chemical equation, neutralization. It's used for titration, and this is how you calculate the titration numbers. A big Ka is a strong acid, a big Kb is a strong base. A strong acid and a strong base make a neutral salt. Weak acid, strong base make acidic. Strong acid, weak base make acidic salt. Weak acid, strong base make basic salt. Acid anhydride plus water makes acid. Base anhydride plus water equals base. So there's lots of chemical reactions. Sort them out, figure them out, and we'll practice. Look at those book connections. And here are the objectives for this PowerPoint. So peace out.